Now, at this stage, since we've understood the graph of sine function, the understanding which you can translate, we can actually also check to cosine and so on. I think it's also important to look at the inverse trigonometric functions, because very soon we're going to be looking at the equations also. Then let's say inverse of function like sine t of y is equal to sine t. I'm going to again exploit our knowledge of graphs. I'm going to exploit the knowledge of graphs. Now, let's say we have something like this. Let's say this is minus pi. Now, the sine curve will come this way, up, down, and so on. I was not very careful here, but I think I need to correct that a bit. I want to correct this thing a bit here. I'll insert my y is equal to x there, and say that is y is equal to x, and then set my sine curve this way, and set it this way. Now, if we were to reflect this curve around the x-axis, you will go this way. You see, guys? Then what happens? Tentatively, this should be y is equal to sine second function of t. But our usual question, is this going to be a function, this curve? Why? It was the vertical test failed, isn't it? So which means then we need to do some kind of transformation here of this thing, isn't it? So what we usually do is this. Check, guys. Check what we do. Now to get the inverse function there, what we normally do is we'll just take this from minus 1 there to 1 somewhere there. Remember the range of sine function, it was going between, though it didn't say it explicitly, but it's clear that the values of sine function are between minus 1 and 1, isn't it? So now we just take it there from minus 1 to 1. Then the rest of the curve, this side, we delete it because it fails to a function. Then that side also at the top, we delete that part, and that. Then you will see in your books, when you get your books, you will see that the inverse of sine curve is more or less something which is like this, from minus 1 to 1. Then you say that is y is equal to sine second function of t. Then again, all what we discussed about inverse will work here. Now what will happen? Sine t, sine of sine second function of t will be equal to t. So what we're going to do now? Then if you've got an equation like sine of t equals to half, you want to know this t, then you need to use this kind of thing, because this is still going to be the same thing as sine t, then sine second function of t. All that will give you the identity function altogether, that kind of composition. Then I'm not going to discuss the inverse of cosine, but I'm asking you to go to your book. You see the curve also is going to be something more or less transformed like this. It's no longer something which runs through the real axis. So the domain of sine, inverse sine, becomes -1 to that. And then you can also check the range there, why does it, how high, how low there does go and how high it goes there. You get this range. Altogether, guys. So now, at this stage, you've got the sine function, you've got the inverse sine function, and you're expected to try to go in and unpack and understand the inverse of cosine, the inverse of tan. But good thing about it, all functions and their inverses, they work exactly the same way, like this. That if you compose a function and its inverse, you will always got the identity. Are we together, guys? Okay. So now, when you operate with your calculators, let's say, let's take this one which you have got there. Let me take this one. Let's say we've got sine of t equals to 0,5. This value is a positive value of sine, and it's 0,5. And the check, there is the sine curve. There is the sine curve. There is the sine curve. Y is equal to sine t. Now we're talking about this value, this function being 0,5. 0,5, if this is 1, if this is 1, 0,5 is somewhere there. Now if we take a horizontal at the level of 0,5, just from 0 to 2 pi, this t is going to be a t somewhere there, and it's going to be a t somewhere there. So within the period 0 to 2 pi, how many solutions are there? 2. Now if you remember what we were discussing yesterday about the angle, sine of any angle in the first quadrant, second quadrant, then that will come in now here. Altogether. So let's draw that sketch a bit now. Let me say dip and get rid of this. I want to draw what you had yesterday, the sketch which you had yesterday. We were around the origin. Let's take our circle to be that. Then if we put 0,5 there, we're talking about that angle, which you can call theta, and let's say theta 0 is what we call a reference angle. Reference angle. That will always give us what? A positive ratio. But we also have got this angle, which is the angle which I'm measuring from here 0 up to there. And that angle, if I use that idea of reflection, that angle, this is theta 0, then that angle is actually pi minus theta 0, the reference angle, isn't it? So now, how do I get into the process of solving this? Even if I don't draw the picture, but I've got the understanding of that, what I'm going to do, this is what I'm going to do. I'm going to say, first of all, let me set this thing to its reference angle. Sine t is 0, 0,5. Then I say, this is sine, second function of sine t is 0, equals to sine, second function of 0,5. Then this side, because of the inverse, I know this is going to give me immediate theta 0. Then I go to my calculator and just punch in second function sine 0,5, depending on the manual of the calculator. Then I get a value. What is it? 30. 30 what? Get what? Ah, you are still using the old-fashioned measure. Pi over 6. Radians. Altogether, that's pi over 6 radians. So now to give my complete solution, I will say now, therefore, my solution to the equation, because of the analysis I did here, my solution to this equation is t equals to pi over 6 radians. Normally we don't write the word radians, you just write pi over 6 altogether. But if somebody wants it, you can write it, it's not a problem. Then, or t equals to pi minus pi over 6 altogether. That is my solution in the during the first cycle from 0 to 2 pi. Now, if I want to give all of the solutions, all of them, I now need to incorporate that this function is periodic 2 pi. So if it's periodic period 2 pi, how many solutions would that equation have? How many? 4. No. If it's periodic, this function repeats every 2 pi, how many solutions would that equation have? Sorry? Guys, these values are going to repeat after 2 pi, after 2 pi, after 2 pi. So how many solutions are there? Sorry? There are plenty. How plenty? The usual word we use is infinity. Though there's a certain guy who now is saying there's nothing called infinity. I don't know what we're going to do next time. But this is infinity. We can say infinity. We can then say the t is equal to half pi over 2 plus 2k pi. And the way k is our integer. K is an integer. If k is 0, sorry, this is wrong, isn't it? Yes or no? That's supposed to be pi over 6. I put the half there, I don't know why. That's slip of a pen. What am I doing there? I'm taking this solution and picking all the 2 pi periods of it, and I'm incorporating them here. And they're infinity, because this set is infinite, isn't it? Then the other solution will be t, I get a value here. What is this? This pi over pi is 6 pi over 6 minus 1 is 5. So this is going to be 5 pi over 6 plus 2k pi, and again k is somewhere there, isn't it? So if k is 0, I get this answer. That. Then it's just giving infinite solutions. But in our everyday work, we're always going to say, solve this equation between 0 to 2 pi or between this and that value. How to get guys? So I think this is the first example of feel of how to work with the trigonometric equations. I think I'm going to stop there and say thank you for being attentive, those who are attentive, and say goodbye.